So welcome back, everyone, for the final talk of the conference. We're very pleased to have Igor from UCLA to tell us all about Kronecker coefficients.
Thank you. Thank you so much. Can you hear me?
Yes.
Yes? Do this. Excellent. Thank you so much for having me. It is a pleasure to see those of you who I can see right now. And hopefully the rest of you who I cannot see can see me and can hear me at least. I'm going to give a talk on Kronecker coefficients. And this is maybe the first public talk I'm giving on Kronecker coefficients, despite working in the area for maybe a long time. And part of the reason is these talks tend to be technical, and I usually like to be nice and friendly and all. It is quite likely that this talk is going to get technical at some point, but there will be no proofs at all. So you can just enjoy, chill and maybe interrupt if you want to ask questions. I'll try to make some jokes and all. It's going to be somewhat lame, but we'll see how it's going to go. So so I got to define Kronecker coefficients, and so apologies to those who've seen this before. The only thing you really need to know is characters of the symmetry group. Yes, there will be jokes, and well, maybe. So Kronecker coefficients are defined by taking a product of two characters and writing them as a sum of characters, and you get some integers that follows immediately from the setup. And the question is, what are these integers? That's all there is. So I'm going to assume that you know enough about characters of the symmetry group, and you know absolutely nothing about Kronecker coefficients. That's how we're going to go. Are we good with the definition? Yes? Good. So let's see. So one thing that follows immediately from definition is the fact that they're symmetric, because you can sort of push one character on the other side, and or equivalently you can write this as this kind of large summation of products of three characters, which implies that the Kronecker coefficients have this S3 symmetry group. And also you can take a tensor product with a signed character and conclude that you can actually take any two of these partitions to be conjugate. So lots of symmetries, some nice mysterious numbers. And so maybe I'll give you an example. This is the only example that you can do in your head. You don't need to know anything. So we have three partitions of three. This is 1, 1, 1. So the characters are 1, 1, 1, 2, 0, 1, 1, minus 1, 1. And so if you multiply two characters of dimension 2, then you get a character 4, 0, 1, which is actually happens to be the sum of three characters. And so since multiplicity of 2, 1 in the product of two ones is 1, then we conclude that this Kronecker coefficient is 1. So we're going to be generalizing ones, so to speak, coming from here. Everyone good with this? It's pretty important. If you don't get this page, you don't get the rest of the talk. So your last chance to ask a question. Okay, anyway, let me recap. We have some numbers which come out of character symmetry group in the following simple manner, and we want to understand as much as possible about that. So what do we want to understand? Well, we want to compute these numbers, whether given explicit formula or understand computational complexity aspects of the problem. We want to decide whether this number is 0 or not 0. If this is sort of a special case of the previous problem, but it's sufficiently important. It has a name called vanishing problem. Another thing we want to do is we want to estimate a Kronecker coefficient, at least on some special cases. And we want to give a combinatorial interpretation for Kronecker coefficients, and that's something we don't know, and it's a classical open problem with a giant amount of history, which I'm not going to cover, basically history of failure, but with a very small amount of success. So what we're going to do is I'm going to talk about all 4 items, all 4 problems, and let me skip almost completely on the history of the problem. Let me just mention 2 highlights and apologies to those who work on Kronecker coefficients that I don't mention you in the history, time as a constraint. So I want to mention that the whole story started with works by Murnaghan back 80 years ago, who introduced Kronecker coefficient, studied the stability, realized that they generalize little Richardson coefficient, and so forth. And another major event, so to speak, happened when Ketan Mulmuli published, 6th installment of his opus magnum geometric complexity theory, where Kronecker coefficient played a major role with a lot of conjectures that could be proved and occasionally disproved, actually often, more often disproved than proved. But either way, this brought a lot of attention to Kronecker coefficients, not only from the point of view of combinatorialists, but also by people in computational complexity theory. So that's all the history I'm gonna tell you, and I'm gonna move on unless you interrupt me. Okay. So let me start with what usually is the hardest part in the talk. I'm gonna, for people in combinatorics, I'm gonna mention a little bit about complexity of computing. And it is pretty important to distinguish 2 types of inputs. So one can sort of think of a partition given in binaries. So if you have a number like 1001, it has, instead of thinking of that as 1001, we think of that having 4 digits. But in unary, you want to think of the size of the partition to be n. And those 2 types of complexity aspects are pretty different. And in many ways, binary is hard. Positive results are harder to prove for binaries, and negative results are harder to prove for unary, and that's what we'll be facing with. So denoted by Cron the problem of computing G lambda mu, and similarly LR, the problem of computing little Richardson coefficient. This is basically just to compare the 2. I'm not gonna tell you what little Richardson coefficients are, but if you read Bruce's book, you know what they are. So let's move on. Is it clear what I'm doing? Yeah, I'm asking complexity problems. And let me just right away tell you 2 results. One is a relatively easy result, a little Richardson coefficient as sharp P complete for binary, and a difficult result that we just proved with Greta, which says that in unary it's also sharp P complete. This is not available yet, maybe in a couple of weeks, but in fact, for little Richardson coefficients, we understand complexity extremely well. For Kronecker coefficients, we sort of understand it. First of all, Kroneckers are harder than little Richardson coefficients. And in binary, this was realized by Burgess and Ickenmeyer. And in unary, it was actually done before us by Ickenmeyer, Mulmuli, and Walter, who are all in the pursuit of geometric complexity theory. So they did show that Kronecker coefficient is sharp P hard in unary as well. So the reason why I'm writing here sharp P hard instead of sharp P complete is because, remember, we don't know if Kronecker coefficients lie in sharp P, because we don't know if they have a combinatorial interpretation. That's the point. And in a positive direction, let me mention a theorem. There are different versions of the theorem, but essentially we're saying that Kronecker coefficients can be computed in polynomial time. For example, if number of rows of all three partitions bounded by, say, 10 or some universal constant. Then there is a polynomial time algorithm to compute that. Does it mean that they have a nice combinatorial interpretation? But there is an polynomial time algorithm which allows you to compute that. And in binary cases, it's pretty easy. In unary case, it's supposed to say in unary, it's very easy. And in binary, it is given by Barwinek's algorithm, which is applied to contingency tables I'm going to show on the next slide. Is this clear what I'm talking about? Any questions at this point?
What's varying in the?
What?
So if you fix all the sizes, aren't there just finitely many partitions?
No. L is the number of parts.
Oh. Yeah. Sorry. Great.
Good point. Everyone good?
Yes, for the Sharpie heart, you use the Turing machine model, right? But for the FP, you use the algebraic model.
No, FP is just basically it's polynomial time for functions rather than a decision problem.
Okay, thank you.
So let's go back to our major open problem, find the combinatorial interpretation. So in the complexity language, this is asking whether the problem of computing Kronecker coefficient lies in sharp P. This is, at least that's my understanding of how the problem should be phrased. If you talk to many people in the field who I actually talk to a lot about this problem, they will always tell you, oh, that's not what we want. We'll want some nice young tableaus and which satisfy nice properties, and they have a good reason why they want it. It's just if you can't formalize what you want, you cannot prove or disprove. I mean, you cannot disprove that. I'm just gonna go with computer science definitions that I do understand. So one important point that I wanted to make is the theorem by Burgess and Ickenmeyer, which is saying that we're very close. Kronecker coefficients may not have a combinatorial interpretation, but they can be written as a difference of two sharp P functions. So in that sense, they're very similar to characters of the symmetric group, because Monogama-Nakayama rule tells you instead of, they can be negative, it just tells you that it's a difference between some positive set of combinatorial object minus some other set of combinatorial object. And the proof follows immediately. The original proof was harder, but the proof I'm giving you follows immediately from this identity. So one can write Kronecker coefficients an alternating sum of the numbers of three-dimensional contingency tables, where CT of alpha, beta, gamma is the number of three-dimensional contingency tables with two-dimensional marginals alpha, beta, and gamma. Okay, I promise you, since I'm not giving proofs, you can choose to believe or disbelieve me, but I promise you this, the proof of this identity is really just a few lines from existing results. It's not particularly difficult at all. And now you can see why it's important to have the lengths to be very small, because then you can think of number of contingency tables as integer points in a finite dimensional polytopes, which you can just count. And so it's important sort of to compare this result with what we know. So Little Richardson, of course, lie in gap greater or equal to 0. That's because Little Richardson do have a combinatorial interpretation. So in fact, they lie in sharp P. And for the unary case, it's Little Richardson rule. And in the binary case, you have to think in terms of Gelfand settling patterns. So again, think of them in terms of integer points and some polytopes. For the Schubert coefficients, which I'm not going to talk about, it actually doesn't follow from most formulas. Because if you take, for example, a formula in Sarah Billy's paper, you have to divide by a certain number, which is not allowed in the definition of GAP P. It has to be really the difference of two Sharpe functions. However, if you dig deep in the literature, there is a formula in a paper by Postnikov and Stanley, which does imply just directly that Schubert coefficients lie in GAP P, and of course they're non-negative. And similarly, one can look for related classical problems. You can take a character and square it. That's immediately non-negative, and basically by definition that lies in GAP P. That is the difference of two Sharpe functions. So in a somewhat more complicated, for a more complicated reason, the sum of the character values are also a non-negative number, which is by Monogamma-Yamaguchi rule, again, is a difference of two Sharpe functions. So, from once you see this list, it sort of becomes unclear. Should you believe that Kronecker is more like Little Richardson, or that Kronecker is more like everything else? And from some point of view, some people believe that, yes, of course, that Kronecker is like Schubert. We're always looking for combinatorial interpretation for Schubert. We should be looking for combinatorial interpretation for Kronecker as well. On the other hand, if you compare it with the character square, I think most sane people would not believe that square of the character has a combinatorial interpretation. It's just a nasty function. So it is quite conceivable that Kronecker is more like character square than like Little Richardson coefficient. That's all I'm going to say about the combinatorial interpretation before I move to bounds. Are there any questions about this? We're switching subjects. Okay, good. So I'm going to start with some very easy bounds, and the proposition 1 follows immediately from definition. So actually, now that I think about it, this is a proof of proposition 1. So indeed, straight from the definition of Kronecker coefficient, remember, it's you take a product of two characters and you write as a sum of Kronecker coefficient times the third character. And this is just a dimension. So straight from the definition, it follows that Kronecker coefficient is bounded by the dimensions of characters lambda, mu, and nu. And that is not a bad bound. So here is another easy bound that you can get in a, I don't know why I have this absolute value here. So Kronecker coefficients are bounded from above by this three-dimensional, by the number of three-dimensional contingency tables corresponding to lambda, mu, nu. And in a different, and similarly, so the reason is this complicated formula over there, which basically writes contingency tables as a sum of Kronecker coefficient times some Koska numbers. And similarly, there is a kind of dual version of this result. Kronecker coefficients are bounded by number of 0, 1 three-dimensional contingency tables with marginals equal to conjugates of those partitions that you have over there. So lambda prime, mu prime, and nu prime. That's those are the only kind of three easy bounds that I have, and the proof is actually not particularly new. This one is due to Ernesto Vallejo, who proved a lot of other results. And this proposition 2 prime is actually very interesting because that was used by Ichenmüller, Müller, and Walter to prove a match that this inequality is actually an equality in some cases. Okay, so so let me give you a few more bounds, which are now more complicated. So one thing that I can do is I can just show that here is a bound that you can understand, anyone can understand, because that's just a product of some powers. So it turns out that if you do have a bound on the number of rows of lambda mu and nu, then Kronecker coefficient is at most this product. Why is that so interesting? I don't know, but that bound turned out to be pretty sharp in many cases. And it doesn't depend much on lambda mu nu. So in some cases, when lambda mu nu are very far from being rectangular, it's not a terrific bound. But when they're very close to be rectangular, that's actually not a bad bound. So in particular, let's take an example when you have sort of a rectangle where there are L rows and each row has length L squared. In this case, the proposition 1 gives you a cubic root of n factorial, which is not a terrible bound. It's better than nothing, but not particularly fantastic bound, because this theorem that we have, actually, in this case, all these ratios are 1. So we have 2 to the n times 2 to the n, which is 4 to the n. So we get a bound on Kronecker coefficient is at most 4 to the n. This shouldn't be here. What we believe is that that in fact this 4 to the n is very close to be tight. That is, in fact, that's asymptotically, it is 4 to the n minus little of n, and there is just no way we can even approach this problem. So let me tell you now about a couple of other bounds that one can get. So instead of looking at trying to bound a particular Kronecker coefficient, one can just try to bound the largest Kronecker coefficient. And bounding the largest Kronecker coefficient turned out to be actually possible to understand the asymptotic almost exactly. So it turns out that the largest Kronecker coefficient is basically square root of n factorial times something which is given by asymptotic of the number of partitions of n. Do you see what I mean? So remember, the Kronecker coefficients are always smaller than maximal dimension of the reducible partition symmetric group, which is roughly square root of n factorial. So we're saying that it's actually tight in the sense that there are triples of partitions where it is square root of n factorial. And so Stanley proved it in 2016, and we somewhat generalized it to show that if you just it suffices to take a maximum over just one of the 3 partitions, then the maximal Kronecker coefficient is going to be at least the product of the product of degrees of the characters divided by square root of n factorial times the number of partitions. And you can see where this asymptotic for the number of partitions comes in from here. So, so I'm not going to tell you how to prove that, but how to prove part 2. But for part 1, there is a magic identity that you might like to prove by yourself. It's actually kind of like a graduate exercise, but a very useful graduate exercise to know that the triple sum of all squares of Kronecker coefficients is actually sum of the alphas. The alphas are the centralizer sizes of all elements. So in particular, it's bigger than the size of the centralizer of identity, which is n factorial. It's not much more than n factorial, but once you have this triple summation, you can conclude from here that at least some of the Kronecker coefficients are going to be at least square root of n factorial divided by some power of number of partitions. And but because this is an identity, you know it has an easy proof, and it does. We have it in our paper with Greta and Damir. Can I move on? Questions at this point? Okay, so let me go to a slightly harder bounds. So unfortunately, I'm going to define what reduced Kronecker coefficients are, and the way to think of them as a limit of the usual Kronecker coefficient. This is a stability property that Murnaghan discovered, is that if you sort of increase the length of the first row, then everything is going to work, and at some point the Kronecker coefficient just stabilize. That's what he proved. And we take this as a definition that there is this limit, and we proved with Greta in a paper just this year. We both wrote and managed to publish it already this year. That turns out that the largest reduced Kronecker coefficient for for triples of partitions whose total sum is at most 3n. So it includes the usual Kronecker coefficients because reduced Kronecker coefficient keep increasing when you keep adding n. So that number is at most square root of n factorial times e to the big O of n. And the result might not be so pretty, but look how pretty is the proof. So in order to understand that, so we basically what we do is we take an identity from a paper by Bowman, Division, and Orellana. And the identity looks a little scary. It has all kinds of summations which are hard to read intentionally. And there are some somewhat more complicated sort of triple little Richardson coefficients and the usual Kronecker coefficients. But once you have such an identity, the point is if you have an identity like that, you can analyze it. And using some bounds in our previous paper, we were able to obtain this maximal for the reduced Kronecker coefficients, and that's something that until recently was out of reach completely. Okay. Good. So let me now tell you conjectural bounds, which are bounds that we don't have, and unfortunately, there's many more of them that we do. I'm just going to tell you a few of them that I particularly like, and I especially like the staircase shape, which is just the shape of a triangle k-1, k-2, dot, 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 up to 1. This is a partition of k just 2. And I would conjecture that Kronecker coefficient in this case is basically square root of n factorial up to an exponential term. There is no way we know how to prove that. There is no way we know even how to approach that. So here is the best bound that we have. And now it is, when you compare this to, I don't even want to say it, this is so embarrassing. So basically the best bound is that it's strictly greater than 0. That's all we know. So you can just, so there's clearly a lot of room for improvement over there. But let me mention why I kind of believe in that. So part of the reason is if instead of looking at the usual Kronecker coefficient, you look at kind of a generalized Kronecker coefficient, which say for 4 partitions, you can define it as a product of 4 characters, multiplicity of 1 and the product of 3 characters. So then we actually know the exact asymptotic. Then it is equal to n factorial. And there is there is a good reason for that, because now when you write it that way, this is basically you take you're looking at a product of 2 squares. And each of the square is a sum of over a lot of partitions, and we know bounds for Kronecker coefficients over there. So in that sense, one should believe this conjecture. Kronecker coefficients tend to grow exactly what you believe that they should. And there's nothing special about staircase shape for this particular theorem. You can take any shape really here whose degree is roughly square root of 1 factorial, and you would be fine. So let me now switch to Saxel conjecture, which is also about the staircase shape. And it's saying that the Kronecker coefficients, when you have staircase, and any mu are actually strictly greater than 0. So when mu is a staircase, that's proved by this theorem. And in fact, there are many other families for which this is known, and it's known for random partition. It's known, and most recently in a kind of breakthrough, beautiful paper by Bessenrod, Bowman, and Sutton, they showed that it's actually one can take here any character of odd degree. And until that paper, I never kind of looked at characters of odd degree. And now that I have, it's kind of interesting. They're very special. Let me emphasize that the staircase shape is the opposite of odd. It actually has the largest power of 2 one can have. That's a little exercise. So the point is, even this kind of basic conjecture that about non-vanishing of Kronecker coefficient, typically they're very, very large. Even that we cannot prove with the current state of art. Can I move on? Any questions about this? Huh. Are you with me? I mean, somehow I lost.
Igor, are you okay? We're with you.
Oh yeah, okay, good. Okay, I guess only one of my computers broke, not the other one. Let's move on then.
That's funny.
You sort of disappeared for a second. Let's see. So so now I want to get close to conclusion, and I want to talk about explicit construction. So as I said, if you look at Kronecker coefficients of the staircase shape, we know basically nothing. But maybe one can make an explicit construction of some triple of shapes for which Kronecker coefficient can be proved to be very large. And by explicit construction, I mean that lambda mu nu can be computed in polynomial time. This is very typical in extremal combinatorics when people ask for a lot of results in extremal combinatorics are proved using kind of probabilistic methods. So these de-randomization problems are very classical in computer science in general, and extremal combinatorics in particular. So notable question is to find an explicit construction of Ramsey graphs. Large Ramsey graphs, and another comment is that it follows from our previous work that one can take triple of partition to have Vershikera log and shape. This is the shape that corresponds to a random permutation. And when you do RSK to a random permutation, you get a certain shape, which is extremely well known. It was first computed by Vershikera and sort of independently by Logan and Shep. And one can take the triple of partition like that to get a very large Kronecker coefficient. However, this is not an explicit construction because essentially we're again using randomization tools. Okay. So what I'm asking is to find completely explicitly triple of partitions for which Kronecker coefficient is very large, and and I have a couple of results that I want to tell you. So the first result is there exists some explicit construction when you can get e to the n to the 2/3. We can't even get an exponential bound. We're nowhere close to the factorial, square root of n factorial. But we can get exponential of n to the 2/3, and that has to do with essentially this kind of it looks like a parabola, a partition, which with very long first row, somewhat shorter second, and so forth. And in that particular case, one can apply proposition 2 that I had before using 0-1 contingency tables. And in this particular, this is a particular case when lower bound is equal to an upper bound, as in Ickenmeyer and others' paper. And in this particular case, one can just show directly that there are this many tableaus of the type that they construct for this purpose. And my final result is a result about 3 squares. This one should basically conjecture that for 3 squares, it's going to be the same story as for 3 staircase shapes, that one should be getting square root of n factorial. And in our most recent paper, this is sort of the best result that we can hope for. Basically says that yeah, you can get exponential to the n to the 1/4, and that uses quite a bit of machinery. It uses semi-group property. It uses it uses early asymptotic results in a particular case for the Kronecker coefficient relating it to Q-binomial coefficient. That's just a lot of work for such a little result. we haven't published that yet. So these 2 are different papers. So that's all I have, really. That's it. Thank you so much.
Thank you. Okay, so questions for Igor?
There's one in the chat.
Yeah.
So yeah, I have a question about the partition of the tensor. So there are many different kind of partitions, and even the tensor rank has so many different definitions. So for this complexity measure, what specific kind of tensor rank is related to?
Not that I know. Let me answer the question in chat also. I can now read that. So VKLS curve is a fantastic curve. You can just compute the whole thing. You can approximate it. It's just that the result saying that it's VKLS curve plus or minus cubic root of n, or n to the 1/6, I forgot. And there is just too much choice. You cannot just go over all of them in polynomial time. So there are some partitions which are close to VKLS curve, which work. Which ones we don't know. The curve is an analytic curve. You have to find some discrete version of that, and we don't know which one works. This is about this. I forgot who asked this question, but oh, Sam. I hope I answered your question.
I have a question. Can you say something about how Jan Zattel fixed on the staircase shape for his conjecture?
Hi, Sheila. Say it again.
Like, was there some insight or something?
About what?
Sorry, I can't. Oh.
Can you just repeat your question? I'm not hearing it very well.
She asked if there was any insight about using staircase shape.
Thank you, Margie.
The question is, why did I choose to use staircase shape in here? There is, or in the Saxel. For the Saxel conjecture, it's likely that you can use any self-conjugate very large shape of dimension, roughly square root of n factorial. This particular is very nice, and there are some combinatorial tools can apply to it. That's why we stuck to that. And well, another reason is when Jan Saxel gave a talk at UCLA, he stated the conjecture in the form: there exists a shape for whose tensor square contains all other. And I asked him, "Do you have a conjecture? Which one?" And he said, "Yes, the staircase." So that's that's why we keep using it. There is no bigger reason.
Thank you very much.
But most likely the square of where is it? Most likely the square of the Kronecker coefficient for a triple of squares contains almost everything, except maybe just a couple small hooks. But we don't know. We don't have any idea why that would be true or would not. But I believe Ernesto checked that it doesn't contain n-1 or something like that.
Thanks.
Well, it's sort of a silly question, but what's known about your original question, Kronecker coefficients, for other families of finite groups, say?
So some of our work we actually were able, some inequalities we can generalize to other finite groups. So essentially they become better when number of conjugacy classes becomes very small. And this is P of n, and you can sort of trace it through some slides that we had. But if you take some, groups, so let me see. I have to go back. It's actually really interesting to see what happens. Let me sort of this summation still works over for every group, every finite group, and it's really interesting to calculate what the sum of the alpha is for the monster. I'm not going to tell you what it is. But when I did the calculation, I couldn't believe my eyes. It took me some sort of thinking and meditation to realize that, yeah, that's kind of obvious. One should be getting that answer. Basically, it's very close to the order of the monster, the sum of the squares of Kronecker coefficients corresponding to the monster. But it's surprisingly close, and we explain it all in a joint paper with Greta and Damir. The specific we have a separate paper what happens for general finite groups. Nothing else is sort of as interesting as symmetric groups. So for everything else we stick to symmetric groups.
So if there are no more questions, let's thank Igor one more time and all of our speakers for this wonderful session.
Okay.